Okay, we are going to start our topic off today with verifying polynomial identities. And we've talked before about the difference of two squares. And for those of you that are doing this distance learning, by now, I want you to be able to recognize this and how to factor it, because that's what we're doing is factoring. That's why we're doing any of this stuff, to either simplify or condense or expand. So when I see this, there's a thing called the difference of squares. So it is when you have a binomial and there is a perfect square here and a perfect square here, and here is the difference. So here's a perfect square, and here's a perfect square. When you see that configuration, it's a pattern. Good mathematicians just recognize patterns. When I see that, I know, oh, what's the perfect square of x squared? Well, it's x. What's the perfect square of 16? It is 4. So when I see this, this is my driver. I know one's going to be plus, one's going to be minus, because when I FOIL that out, I get x squared plus 4x minus 4x minus 16, and those cancel out, and I'm left with x squared minus 16. So anytime I see this, x squared minus 81, bingo, perfect square, x plus 9, x minus 9. What about a squared minus p squared? Bingo, a plus p, sorry about that writing, a minus p. What about a squared plus 25? Perfect square, but it's not a difference. So no, that won't work. What if I have 4b squared minus 49? Y to the 4th. Looks a little trickier, but it really isn't. Is there a perfect square here? Yes. 2 and also b. Is there a perfect square here? I'll work with the numbers first. 7, and then the square of perfect square of y to the 4th is y squared. One will be positive, one will be negative. So when we talk about special cases, difference of two squares, that's what we're talking about. And it can be factored this way. So we could write it, x squared minus a squared is equal to x plus a times x minus a. Polynomial identity is just when we are equating one polynomial identity on one side of the equation equal to another. So this is an example of one. We would need to multiply x plus a times x plus a. That's what this is. And when you do that, you get x squared plus ax plus xa plus a squared. And I hope y'all realize these are the same thing. It doesn't matter if I write it a times x or x times a, but when I order it, you write it in alphabetical order. So a comes before x. So we get this, which is what we have right here. And then we're going to subtract from that x minus a times x minus a, because that is what this is right here. And we get x squared minus 2ax plus a squared, which is what they have right here. Don't forget this negative will change the sign of all these, so this becomes negative x squared. This becomes negative 2ax, this becomes a squared, negative a squared, and then I'm going to cancel out anything because that's a positive, that's a negative, positive a squared minus a squared. So I'm left with 2ax and 2ax, which is 4ax, equals 4ax. That's what it means when it says that you are going to equate one polynomial quantity to another, and you set those equal and condense until you can find out, are they the same? So my question to you is, are those the same thing? Because we just did this on the prior page where we multiplied that out. Over here, that's what we did, but we had x minus a or x plus a, and that's what we got. X plus a is equal to this quantity. This is still just a squared plus b squared. Are those the same? No. So just because this is a quantity squared does not mean it's this. And if you ever get stuck, just substitute a value in. Let's say that a is 3 and b is 2. So let's try this. 3 squared plus 2 squared, does that equal 3 plus 2 squared? Well, this is 5. 5 squared is 25. This is 9 plus 4. So is 13 equal to 25? No. So if you ever get stuck and have one of those ACT questions where it's just all variables, try plugging in a number, assigning a variable a number and plugging it in, and see if it makes your statement or equation true. What you are going to have to do now is prove or show that this is equal to this. So you are going to take a and multiply by each of these terms. And then you will take b, or negative b, however you want to think of it, and multiply by those terms. And prove or show, are they the same? Just like that's what they were doing over here. We're wanting to prove that this is equal to that. So we take a times a squared, and then you take a times negative ab, a times b squared, then you take b times b squared, b times negative ab, and then b times b squared. That's a cubed. This is negative a squared b. This is ab squared. This is b a squared. This is negative a b squared plus b cubed. You're always going to have the same exponents on the end when you have this kind of binomial times a trinomial. A cubed, let's see what we can combine. Here is an a squared b, and here is an a squared b. It doesn't matter that the b is listed first. So now we're going to have a cubed minus, what happens with those? They cancel out. So that cancels out and that cancels out. What happens here? We have ab squared and negative ab squared. What happens to those? They also cancel out, and it really can show you like this. A squared b, and this is negative ab squared. Those are all going to cancel out here, 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 and so you are left with a cubed plus b cubed. So that is a true statement. Now I want to talk with you about Pascal's triangle. Notice, this is how these rows are ordered. Row 0, row 1, 2, 3, 4, 5, and 6. Because this is really like saying x to the 0 power. What is x to the 0 power? It's 1. And this could be like x to the first power, x to the second, x to the third. That's what this means. Okay, so you start out with a 1 here, and going left or right, the only thing that can go here is also a 1 and a 1. Now, going from here, I could go to 2 different places. I could go here, and this one could also be split into 2 different places, left or right. Well, this is going to be 1, 2, 1, because there are 2 possibilities here. Well, let's put 1 here. That can only go left one way. But what do you get here? And you are adding these together, just like you added here to get this. You're adding what? 1 and 1, and you get 2. Now we're going to add 1 and 2, and we get 3. Here, you're going to add 2 and 1 and get 3. And then we're just going to have 1 there. Let's continue that same pattern. Ten, 10, 5, and 1. 1, 6, 15, 20, 15, 6, 1. So we could expand this on out further as many times as we wanted, but that's what Pascal's triangle is. So let's come back over here and let's look at these questions and see if we can answer them. So I'm going to fill this in and y'all read these questions right here. So this is 1. Okay, look for patterns in the tree diagram. So here's our tree. What patterns do you notice? I hope you were able to see that there is a 1 in the first branch of this tree and also in the last branch. And for every other node, for here, it's always what? The sum of the 2 values above it. And we have filled in rows 5 and 6. So now let's look over here to see how we're actually going to relate this to anything. And I'm going to recreate this. You can just look back at yours. Okay, and this is 0. This is row 1, row 2, row 3, row 4, row 5. That's when we have, anything raised to the 0 power, anything raised to the 1 power. All right, so here, a plus b to the 0 is 1, that's what we have here. What is a plus b to the first power? It's just a plus b. What is a plus b to the second power? Which we've already done that on the prior page. A squared plus